Welcome to the debate. For years, the intellectual engine of machine learning research has, really centered on designing powerful neural architectures and crafting efficient optimization algorithms. Today, we delve into a provocative new theoretical framework, nested learning, or NL. This paradigm suggests that deep learning systems aren't just sequential stacks of layers, but are fundamentally integrated systems composed of nested, multi-level optimization problems.
Exactly. And the central question for our discussion today is this. Does the nested learning paradigm represent a truly necessary fundamental shift in how we conceptualize and build machine learning models? Is it, the theoretical breakthrough we need for genuinely adaptive next-generation systems?
Or S, is it primarily a powerful, mathematically rigorous, white box reinterpretation, maybe a unification of existing deep learning concepts and architectural innovations?
That's the tension.
Right. So I'll be arguing that NL provides the essential theoretical mandate required for enabling true continual learning and designing genuinely self-modifying systems. Basically, finally breaking that static barrier we see in current large language models.
And I'll present the case that NL, while yes, profoundly insightful and absolutely invaluable for its conceptual clarity, serves mainly to formalize these deep connections to established, powerful concepts, things like fast-weight programs and preconditioning, offering a powerful descriptive language rather than introducing an entirely new operational paradigm for computation.
Okay, so my core premise is really rooted in the functional necessity we see out there in the field. Current large language models, after their initial massive pre-training, they become largely static. They suffer from what you could almost call anterograde amnesia, meaning, new knowledge acquired during runtime, or, in context, it doesn't effectively impact the fundamental, long-term memory parameters, those feed-forward layers. Nested learning, I argue, is the theoretical mechanism that resolves this static barrier. It moves beyond the traditional sort of flattened view of deep learning by structurally and coherently representing the model as a set of nested optimization problems, each operating with its own distinct context flow. This decomposition finds its inspiration in neurophysiological evidence. The multi-timescale update mechanisms, the varying frequency processing seen in the human brain, things like delta, theta, alpha, and gamma waves. NL is, I believe, the path to designing learning algorithms with multiple defined levels of processing. And this directly results in superior adaptable memory systems and enables higher-order in-context learning abilities. It's the structural framework that unlocks true self-modification.
Okay, I definitely see why you think that, and you're emphasizing the critical need for continual, robust adaptation. Absolutely. The inability of these large static models to integrate new, long-term knowledge is, it's a real problem. However, I'd frame the nature of NL's contribution a bit differently, more as one of unparalleled clarity and synthesis. The NL framework is frankly brilliant at demonstrating that existing deep learning methods succeed because they efficiently learn from data through, as the paper puts it, compressing their own context flow. It essentially transforms the black box into a mathematically transparent system. But when we examine the framework's own powerful derivations, we find this decomposition often reveals really explicit connections to previously established, albeit perhaps less formalized, concepts.
Standard training process of even a simple multi-layer perceptron and MLP using stochastic gradient descent with momentum isn't a single process. It's mathematically proven to be a two-level optimization process. And the paper itself states this process is, quote, closely related to fast-weight programs, where the weight update, the slow network, is generated by the momentum term, which acts as the fast network. So therefore, I see NL as less of a completely new blueprint and more of a powerful Rosetta Stone, if you will. It provides the optimal language to classify, analyze, and mathematically describe internal deep learning dynamics that were already effective without necessarily introducing entirely new computational primitives.
I can concede that NL provides an unmatched descriptive language, certainly. But I'm not convinced that its contribution just stops at, superior taxonomy. The theory offers concrete, innovative paths forward that were simply obscured when we view deep learning through that older monolithic lens. I mean, if NL is such a brilliant classification tool, let's see how that classification power enables us to build something fundamentally new. And I argue it does, starting right with how we conceptualize the optimization process itself. NL formalizes optimizers like Atom or SGD with momentum, not as these abstract algebraic functions, but as associative memory modules that compress past gradient information into their internal parameters.
Okay.
And crucially, this perspective gives us a mandate, a theoretical justification to propose substantive architectural advancements, like deep optimizers. For example, the momentum term is traditionally just a simple, linear, matrix-valued memory. NL suggests, well, why not extend this to a full neural network, perhaps an MLP, creating what they term deep momentum gradient descent, or DMGD. This gives the momentum module itself increased learning capacity to better capture and manage complex underlying gradient dynamics. Or consider using a more expressive internal objective, like a delta rule-based update. This allows the memory module to more judiciously manage its limited capacity and improve how it memorizes the gradient history. These are, I think, substantive algorithmic improvements derived directly from the NL theoretical lens. They feel like fundamentally new design choices enabled by this nested white box view.
That's a fascinating point, especially regarding the delta rule update and the concept of deep optimizers, which I agree certainly sounds like a structural shift. However, when we dig into the resultant mathematics, the actual operations happening on the gradient flow, I would argue the novelty lies more in the unification rather than the creation of truly novel operational mechanics. While NL brilliantly formalizes momentum as a type of keyless associative memory, the specific mathematical extensions often map back quite neatly to known techniques, even under this elegant formalism. For instance, the framework's extension for more expressive association, which introduces an input-dependent transformation to the stored gradient, well, it's shown in the paper to be explicitly equivalent to using preconditioning within momentum-based gradient descent. And preconditioning, as an established method, well, it attempts to normalize the optimization landscape. NL provides the insight that this means the momentum term is acting as a memory mapping for the preconditioning matrix, but the operational result is familiar and achievable within the existing deep learning formalism. Even applying nonlinearity on the optimizer's output, which sounds pretty radical, results in optimizers that are shown to be mathematically equivalent to other established adaptive learning rate methods already out there in the literature. So NL therefore provides perhaps the most elegant and transparent language to unify and engineer these advanced optimization techniques by exposing their underlying memory structures. But the foundational mathematical operations, gradient descent, adaptive learning rates, they remain pretty central to the whole process.
Okay, I agree on the unifying power of the language, but I think the most compelling argument for NLL's status as a paradigm shift really lies in the architectural domain. And this leads directly to the Continuum Memory System, or CMS, utilized in models like HOPE. This is where the structural transformation feels, well, undeniable to me. The conventional transformer block is structurally limited. The paper itself acknowledges this, calling it a special instance of CMS, where the number of frequency domains, K, is just one. In sharp contrast, CMS is formalized as a true chain of MLP blocks, where each block is intrinsically associated with unique, distinct update frequency and a specific chunk size. This structural hierarchy allows the model to process information with different levels of abstraction and timescale simultaneously. And this fundamentally addresses that issue of LLM stasis we talked about. This hierarchy, based on the definition of update frequency in the paper, is a rigorous, direct implementation of the NL paradigm. It creates layers that are intrinsically defined by their temporal update rhythm, which feels far more profound than just typical layer stacking or algorithmic adjustments. You have low-frequency layers for long-term knowledge consolidation, high-frequency layers handling rapid context fusion. It's the architectural realization of these nested optimization problems.
The CMS approach is unquestionably a powerful and effective architectural design. The results show it provides superior performance by separating that long-term knowledge consolidation from the high-frequency contextual updates, which is, quite similar to system consolidation ideas in neuroscience. However, let's scrutinize the mechanism of enforcement here. The definition of frequency itself merely orders components based on their update rate per unit of computational time or dependency. The key mechanism that actually creates the hierarchy in CMS seems highly engineered. The parameters of the slower layers are updated only if the current time step is congruent to 0 modulo some predefined large chunk size. So, to use an analogy maybe for our listeners, CMS essentially means the model utilizes different time horizons for different parts of its memory. High-frequency layers are like a fast-moving scratch pad, may be updated every single step, a chunk size of 1.
Size is the control knob. Now, while this sophisticated parameter scheduling enables multi-timescale updates and is highly effective, couldn't it be seen as an advanced technique for recurrent design and parameter scheduling, where the explicit levels are enforced by a computational choice rather than by fundamentally redefining the core computational primitives? It feels consistent with the trajectory we've seen in highly optimized recurrent models.
But that enforcement mechanism is the shift, precisely because it is theoretically mandated by NLL. It's not just arbitrary engineering that happened to stumble upon a good schedule. It's presented as the structural consequence of decomposing the model into these nested optimization problems, specifically tailored to mirror the brain's approach to memory consolidation. The theory, in this view, dictates the architecture. Furthermore, NLL provides crucial clarity by making this rigorous mathematical distinction between memory, defined as a neural update caused by an input, and learning, which is the higher-level process for acquiring effective and useful memory, by showing that the training process itself acts as an associative memory system, mapping input data to its local surprise signal in representation space. NLL makes the model's inner learning loop mathematically transparent. This integrated system of nested optimization problems is what allows architectures like HOPE to be self-referential. It learns how to modify itself by observing and optimizing its own update algorithm. And this meta-learning capacity, built on a transparent theoretical foundation, is, I argue, why we see such superior performance in complex reasoning and language modeling tasks reported in the paper.
That's a compelling argument, definitely, focusing on the definitional clarity and that self-referential capacity of the derived models. And I absolutely acknowledge that the NL framework's ability to articulate the process of learning how to learn is, well, unmatched. However, we still have to return to the underlying math, right? The core associative memory formulation and its application to sequence models or linear attention, it remains highly related to existing formulations found in the literature, particularly work focused on Kest time memorization and fast weight programming. We've understood for a while now that the attention mechanism in a transformer is fundamentally a memory update rule.
Now, while NL provides this unified formalism that beautifully connects the parameter update of the projection layers, the slow weights, and the memory update of the attention block, the fast weights, the core underlying process still relies on the gradient flow that the deep learning framework already established. The advancements, like the new gradient descent variant used in HOPE, which employs a specific input-dependent scaling, these are powerful mathematical extensions applied within the multi-level structure defined by NL, certainly, but they don't necessarily invalidate the fundamental efficacy of the deep learning architecture being analyzed. So is NL a descriptive theory of unparalleled power? Absolutely. But we must be careful not to mistake elegant description for a radical operational departure from the fundamentals of gradient descent computation.
I still maintain that the transparency NL offers is inherently structural because it dictates these design principles. The static nature of current large language models necessitates, I think, a theoretical breakthrough beyond just incremental scaling. Nested learning offers this by structurally decomposing deep neural networks into these nested optimization problems, operating on their own timescales and context flows. This allows us then to rigorously design specialized, self-adapting components from deep optimizers to the continuum memory system, leading to models that are fundamentally more adaptable and self-modifying. It feels like moving from interpreting existing architecture to actually architecting interpretation.
And I'd conclude by saying NL is, without question, a massive leap forward in conceptual clarity. It transforms the black box of deep learning into this mathematically white box system, where internal gradient flows and multi-time scale updates become transparent and, crucially, engineerable. While it brilliantly unifies advanced concepts, momentum, preconditioning, the delta rule, fast weight programming, under one theoretical umbrella, the resulting performance gains still appear to stem from specific, powerful architectural engineering choices, like those multi-time scale memory modules in CMS. NL provides the optimal, rigorous foundation to describe and develop these choices. And I think the value of this kind of intellectual disagreement is clear. It really sharpens our understanding of the exact relationship between these rigorous conceptual frameworks and the practical, high-performance implementations that define the cutting edge of advanced AI research.
All right, welcome to The Explainer. Today we're going to dig into a really fascinating paper that, it kind of challenges the entire idea of deep learning. It puts forward this radical new way of thinking about how AI learns, a concept they're calling nested learning. So let's kick things off with a bit of a puzzle. You've probably noticed this yourself. Large language models, they're incredibly powerful, right? But once they're trained and out in the world, they're pretty much frozen in time. They can't really learn from their new experiences or conversations in any meaningful, long-term way. So what's going on there?
The paper offers this absolutely brilliant analogy to explain what's happening. It's like these models have a form of anterograde amnesia. That's the condition where you just can't form new long-term memories. So all of their knowledge is basically stuck between two extremes. The stuff they learned way back during pre-training, that's the distant past, and whatever they can see in their immediate context window, which is like the super fleeting present. There's nothing in between.
Okay, so how do we even begin to fix this? Well, here's our game plan. We're going to break down the paper's solution in 5 steps. We'll start with AI's memory problem, look to the brain for some clues, and then get into the main idea, nested learning. After that, we'll see how even optimizers are learners, and then we'll check out a new architecture called Hope that puts it all into practice.
All right, Section 1, AI's memory problem. So here's the deal. The fundamental issue is that what we've been doing, just stacking more and more layers to make models deeper, it doesn't actually solve this core problem of continual learning. Yeah, it adds more raw capacity, but it doesn't fix the model's inability to adapt and actually keep new knowledge. So, to find a completely new way forward, the researchers realized that they couldn't just look for a slightly better algorithm. No, they needed a whole new paradigm. And where did they look for inspiration? Well, they went to the best learning machine we know of, the human brain.
Okay, this is really, really cool. What this illustrates is a key principle of how our brains actually work. See, the brain doesn't have one single master clock ticking away. Instead, different parts of it, different neural circuits, they all update at different speeds, at different frequencies. You can kind of think of these like brainwaves. You've got these really fast waves for handling what's happening right now, and then you've got these much slower waves for consolidating information over the long term. And it's this multi-timescale updating that's absolutely crucial for how efficient and flexible our brains are.
And that idea right there, that brain-inspired concept of multi-speed updates, that is the absolute heart of this whole nested learning thing. In fact, the paper makes a pretty bold claim. It says that what we call deep learning is actually an illusion. It's a flattened, way too simple picture of what's really going on. The true structure, they argue, is nested. Okay, so to really get this, we have to understand a core concept from the paper, and that's associative memory. Now, in simple terms, just think of it as a system that learns to connect things, like mapping a set of keys to a set of values. The big idea in nested learning is that every single part of a neural network, I'm talking everything from the attention layers to the optimizer itself, is basically one of these associative memory systems. And each one is just trying to compress information that's relevant to it.
So this picture on the left, this is probably how you're used to seeing a model. It's just a flat, linear stack of blocks, right? And look, it's a useful diagram, but it hides what's really happening inside. It treats the training process, all the gradient updates and stuff, as this totally separate external thing that happens to the model.
But now look at the right side. This is the nested learning view, and it completely flips that on its head. It reveals this hidden structure. It's not a flat line at all. It's a hierarchy of learning modules. You can see that each level is basically its own little optimization problem, updating its own memory at its own speed. Hey, just like those brainwaves we were talking about. And what's really powerful about this view is that it makes the whole internal process transparent, or as the paper calls it, mathematically, a white box.
Okay, and this is where, for me, the insight gets really, really interesting. This whole nested idea. It doesn't just apply to the model's layers. Nope. It extends all the way down to the very optimizers we use to train these things.
So here's the crucial point. Think about a really basic optimizer, like standard gradient descent. From this new perspective, that's just a one-level learning process. Simple enough. But now, let's add momentum. We usually think of that momentum term as just a little tweak to speed things up, right? Well, nested learning says it's actually a second, faster, nested learning system. It's its own little associative memory, and its entire job is to learn and compress the history of past gradients to help the main, outer system learn better. That's a huge shift in thinking.
So, look, this isn't just some abstract academic theory. This framework actually leads to completely new ways of designing AI architectures. And to prove it, the paper introduces a brand new model built entirely on these principles, and it's called HOPE. This comparison really tells the whole story. So on the right, you've got your standard transformer. It has one big feed-forward network that's kind of the part of the model that holds and processes its knowledge, and that acts as its long-term memory. It gets updated really slowly, basically only during that initial pre-training. But now look left, at HOPE. It doesn't have one, it has multiple feed-forward networks, and each one is updating at a different speed, from super fast to super slow. This is a direct, practical implementation of that multi-timescale brain-like principle we talked about earlier.
So, the million-dollar question, how does it actually perform? Well, the results are really promising. When they put it to the test on standard language and reasoning benchmarks, the HOP model showed seriously strong performance. In fact, it outperformed other modern architectures, including a really tough transformer baseline. So this tells us the nested learning idea isn't just a cool theory, it's actually effective in practice.
Okay, so let's boil this all down. What are the key things to take away from this? First, that amnesia analogy. That's a really powerful way to think about the limits of today's AI. Second, nested learning gives us this completely new lens. We stop seeing AI as just a deep stack and start seeing it as a dynamic, multi-level system of learners, all running at different speeds, a lot like our own brains. And remember, this view shows us that learning is happening everywhere, even inside our optimizers. And finally, this isn't just a thought experiment. New architectures like HOPE are proving that this is a real, viable path forward.
And this really leaves us with a pretty provocative question, doesn't it? This whole shift in thinking, from deep to nested, it makes you wonder, if we start designing AI not just with more layers, but with more levels of learning, each with its own speed, its own clock, are we finally actually on the path to building an AI that can learn continuously, the way a living thing does?